All right, so now it's okay. All right. There is no I used to teach here. No, they also removed that one. The good side is I can just walk in wherever I can. Now let's try this one this time. Okay, so this is again today is going to be groundwater. This is the only class on groundwater. So we'll learn both about quantity as well as quality. So just few announcement. Homework 4 is due not this next Thursday, this Thursday now. And this everything long question up to this homework is part of the midterms. Okay, so that's why it's very important that you work on those. There are few questions on homework 4 that you could not solve without this class today. So that's why those last two questions you learn how to solve today. Again, difficulty in understanding any of them, attend office hour, my office hour, TA office hour, TA discussion sessions, ask those questions so that you know exactly how to solve those. We're a little bit behind in the syllabus. Is supposed to be groundwater last class, but that's fine because we have still one more extra week for midterms before the midterms. So that means we should be able to catch up. But either way, in the very thing, the first 5 week, whatever cover is going to be in your midterms, which is on the week 7. So week 6, mostly your preparation week. Okay. All right. So learning objective, groundwater. So again, we are going to emphasize on groundwater quality. There is a different class on groundwater itself. So if you take introduction to water resource engineering, there you learn more about quantity. So I'll try to minimize as less overlap we can. So that's why just briefly cover those. Again, why it is important. The very beginning, you know that even though it's not rain today or this week, we'll get a lot of flooding. At the same time, we cannot capture them. So that means we are going to waste those water. And so the real storage or natural storage is groundwater. If it rains slowly for throughout the year, those water are more likely to be available for groundwater. So slowly percolate into groundwater, and that's where we collect and drink them or use them for different purpose. So, one of the study over here, he says that it's in UC Riverside. There's a researcher, they found that the amount of groundwater supplies we have that we are going to lose because of drought is not going to recover ever. Okay. And why is the case? How they find that out? If you estimate that, and we'll learn a little bit about it today. So those concepts are very important for you to understand this kind of news or research. So let's first go through the groundwater quantity. How do we know how much water we have? All right, so if you see here, groundwater is basically that you don't see, it's trapped in soil, but every water that trapped in soil, we don't call groundwater. For instance, if you dig just 1 feet, you might see some moisture in soil, but that's not groundwater. Groundwater is saturated zone, means if you keep digging, after a point, you'll start if you make a well, you'll start seeing water, and water is constantly at certain level. That's where you hit the groundwater, means completely saturated, and that's the level of the well water that would be. So if you draw around some water out of it, eventually that well will be filled again up to that height. That's basically groundwater. Groundwater is, you see over here, this line over here, you see, that's the groundwater table. Okay. If I show it in the view over here, so this is groundwater table. So if you keep digging, that's the location you will hit groundwater. So groundwater is a very small percentage of fresh water we have. In fact, whatever water we have, only 1% or less is really available for us to use. And that's actually more than enough. for all our use. The issue is that many locations where you need most of the water, those water are not available there. For instance, Los Angeles, groundwater is limited here, the amount of groundwater, but the amount we need is a lot more, 10, 15 or 20 times more than what is there, or even 100 times. So where do you get that water from? So some you supplement by surface water, some you supplement by other way. But so that's the critical aspect of here. So think of groundwater as your nature storage. Like a lot of times when you don't have enough water, you put in a bucket and store it. Imagine that one day in your apartment, they says that there will be no supply of water for next 24 hours. So typically what people do is they whatever bucket or storage container they have, they put those water. And so groundwater is kind of a nature storage. So all the water that comes from rain, distributed in surface water, some of them percolate into ground and stay there and move slowly. So those kind of storage that we can always tap into. But if you remove many of them or most of them, then obviously it takes a long time for them to refill. And what makes them to refill and where you can dig, all that stuff is in the first few minutes we are going to learn. So aquifer is the material, one of the key terms that a lot of times you will see is called aquifer. So that's basically another way of saying is the soil, portion of the soil that's filled with water or groundwater that we can tap into. So there are two types of aquifer, just for definitions, confined and unconfined. So again, we are living here, this is the surface, and then every time there is a rainfall, water will move from here and slowly move into ground until it hit the water tables. It's called water table. The reason is that everything below it is completely saturated. There is no air in the soil. Above the water table, the soil pores are filled with air as well as water. But below water tables, everything filled with water. So that means all entire pore are filled with water. So this is saturated zone, or we call groundwater here. So everything below it is we call groundwater aquifer. Okay, and that groundwater aquifer could have two different types. One is confined, another is unconfined. The reason why it is important is because when you try to draw water out of it, how much you can draw, it depends on either of the design, whether confined or unconfined, or how far if you take water out, how far the water table will drop. It also depends on both type of aquifer. So let's see what is unconfined aquifer. Here, if you see over here, water table is above water table, you have soil. And if you pour more water, that might also rise. That means, it's not restricted in the one side. On the bottom side, it seems like, it's restricted, but above here, it can expand. So that's unconfined aquifer. Another example is here. This is very clear here. So on the top, this is unsaturated zone over here. Let me put in. So this is all unsaturated zone. And this is unconfined aquifer. It means that at least one end is open to the not atmosphere, open for water to move in or percolate into the aquifer. So that means this is just a soil, maybe similar type of soil, but filled with air as well as water. So that means water can move from top to bottom. So this end, water can move. But below here, this layer, water cannot move. The reason is it's very hard clay surface. It has very small pores that doesn't allow water to move through it. So it's more like think of a container, open container. With one end you can pour, other end water cannot go. Yes. It's hard rock, mostly clay. So it's basically clay. We'll understand why clay doesn't allow water to move. So think of it like a very compact, non-porous media. So water won't move across. So water cannot move across this layer. If you that's why it's called unconfined. Okay. And the advantage of unconfined aquifer is that you can always refill very quickly, because all you have to do is allow more infiltration to take place above it. So if you have a heavy rainfall here, there is an unconfined aquifer below underground. That means that rainfall, because of rainfall, the unconfined aquifer will start filling more water because the water can come in. So that means if you have a heavy rainfall or weather can immediately affect the unconfined aquifer water levels, okay, because you can, or that location can be affected very easily. Whereas confined, if you look at down here, this is also clay. Now what we have is in both ends, water cannot move out. So that means where this water comes from to begin with. If it can't, water cannot move in from down, from bottom to or top. This is called a confined aquifer, but as you see, if you move across, this is coming from mountain. Okay, so for instance, many other confined aquifer here, maybe the water comes from Colorado Rocky Mountains over there. So it takes many years, sometimes thousands of years, for water to move from that to here. So this is very precious water. So that means if you draw down or remove most of the water, it takes many years for the water to refill, because nothing you can do there that change the water levels. It changed by upstream over in the wherever that aquifer is open. All right, so that's the key difference. The things that you have to remember is unconfined aquifer is can change based on the local climate, whereas on confined aquifer can't, because the opening is way far from where you are located. And so these are different wells. So that's all. All right, so now I have, this is a quiz question just based on what you learned. Which aquifer would be influenced by rainfall at the local level, unconfined or confined? So raise your hand if it is A. Can see. Now we can see nobody. What about B? Fantastic. See, very early you are all here listening everything I say. I'll do the same quiz again, different questions. Towards the end of the class, you will see that 50% will not be able to answer. And that's not your fault. It's just 2-hour class. That's the effect. All right. So now the key question is, how do you know that, like I said, because of drought, some of the water that you draw will never be refilled again. The reason, the answer lies here. So we'll see why it is the case. So how much groundwater you have in any soil depends on how much pore space you have. And that pore space is defined by porosity. Porosity is just a measure of the pore space in aquifer. Okay, so this is pore space in aquifer. So how much pore space is there? So if you take, imagine if you dig 1 cubic feet of soil, just take it outside. It's not everything is empty. There are soil grain that occupies most of the space, but there are also within the soil grain you have space in between. It's like if you try to pack few solid balls into a bucket, within the ball or between the balls there are gaps. So those are the pore space that water fill in. So if you, what I'm saying is, if you imagine there is a two grain of let's see, this is soil, but so this is the, imagine this is soil, okay, and water is going to fill up over here. So this is your pore, okay, pore space. There could be also pore space in between grain, intra-grain, because if the grain itself is porous, then inside there are water. So mostly, if you are calculating a porosity, that's basically volume of pore space or void space divided by total volume, that 1 cubic feet of soil that you dig. So that's the unit. Okay. And now this pore space is not constant. It turned out the pore space that you have in aquifer is filled with water, and that water, if you withdraw it, this water itself is also taking a lot of pressure. The soil above it is applying a lot of pressure. So this water prevents the pore space to collapse. So if you take lots of water out of it, the pore space is going to collapse because there is no water inside it, and they will collapse eventually. It doesn't happen immediately, but if you take enough water, and then this pore space collapse, that means even later time you fill the water, that space is no longer available. So that means if you keep drawing water in California, after a point, this pore space become very small. You can't recover them anymore. So that's why in a drought time, people take a lot of water out of this pore space, and it come to a point where it's so critical that it's collapsing the pores. So that's why they found that how much water you have drawn and how much pore space you now is unrecoverable. So that's the reason they said some of the pore space that we already take it out is not going to be available anymore in our lifetime or even in future, because who is going to lift the tons and tons of soil? Can't. Nature has its own way. Unless there is an earthquake, things move up. Otherwise, things are already done. And so there is another terms in your FE exam they may ask is specific yield. So these are short question in your FE exam or fundamental of engineering exams. Just know the concept so that you know what those are. So specific yield is the amount of water that can be drained from the pore space. For instance, here, if imagine you take a bottles and fill with sand and then pour water. Whatever amount of water that can fill in is the pore space that is available, because assuming that all air gone. Now you drill a hole at the bottom and let it drain. You'll see that whatever water you we put it, not everything came out. There's some water remain behind. The reason is water can stick on the walls, or capillary force can also withdraw hold some of the water. So that's the reason if the pore space is very small, not all water can be drained by gravity. So specific yield is basically a measure of how much fraction of that pore space can be drained by gravity. So that basically the answer, it could be, it's always between 0 to 1. Specific yield. 1 means 100% of water you can drain. 0 means none of them. Ideally, it's not necessarily 0 ever. So if the reason why it is not equal to 1 is because soil made out of very fine particles, and those fine particles, as you see, if you remember physics or capillary, or if you put a straw when you drink water and the straw size is very small, you will see that water itself rise. That's because of capillary. Okay. The straw typically used is very wide, so it's not really capillary, you don't see it. But imagine making that straw diameter very small. The moment you put it, the water will rise immediately. So capillary is the reason why if you put, let's say, imagine you take your paper towels and put it on a lot of water, a little bit water, and you put on top of it. It's all soaked inside. The reason is capillary is the action. Okay. So because of that capillary, that's the pressure that water hold inside the small fine particles. And those water will not be withdrawn by gravity because the pressure that hold is much too high than gravitational pull. So that's the reason this specific yield is all less than 1. And specific retention is basically 1 minus specific yield. That means everything that you can recover is specific retention. That means that's the water that will never recover. So why it is important? The reason it's important because every time you try to get water from groundwater, this will help you determine how much quantity of groundwater you can withdraw from aquifer. So you have to account for not just porosity, also specific yield. Porosity means maximum amount of water that can be stored. Specific yield is fraction of that stored water can be removed or withdrawn by gravity. Okay, or you can pump out those. So these are just a practical terms for you to understand. All right, so let's one example. So this is a short question in exams. For an aquifer of a sand having characteristic given on table 1.11, so this is all from your book. What volume of water would be stored in a saturated column with a cross-sectional area equal to 1 square meter? So it's saying that if you take a column, if you dig a soil with this soil column with 1 meter, this area is 1 square meters, and the height or the depth is 2 meter. Imagine you dig that cylinder out of groundwater aquifer. How much water could be extracted from this from that volume? So it's saying if you imagine you want to drain water from this area, this soil aquifer area, how much water you can drain. First, you have to calculate how much water is there to begin with. So that's porosity. And then if you know the specific yield, that fraction of the porosity is what takes that the amount of water you can drain. So amount extracted, so volume of water extracted as you see, this is specific yield is basically volume drained or extracted divided by total volume of water in aquifer, which is basically the porosity or the so that means specific yield time volume of water. Now volume of water, you know that based on this previous formula of porosity, void space is filled with water. So this is water fills this void, and this is the total volume. Okay. So volume of water, that means if you this is volume of water, okay. But assuming the void space is filled with water, because you can't put water in other places. So that's porosity times total volume using that equation. Again, this is porosity. This is specific yield. So Sy times porosity times total volume is basically surface area times the height or depth. So volume is area times depth. This is depth, this is area. All right, so it says sand. So if you see sand here, the numbers are given. Porosity is 34%. Specific yield is 25%. So 0.25. That means 25% of the total volume can be drained. Okay. And then porosity is 34%, which is 0.34. That means 34% of the total volume is void space. where water can fill, and total volume is area is 1 square meter times 2 meter. So that would be, who gets this number? 0.25 times 0.34 times 1 times 2. All right, so that's going to be in 0.17. And if I ask what is in liter, which is a lot of times I ask, you can change 1 meter cube is 1000 liter. So that would be okay. So this is a typical 2-point questions in midterms. Okay. All right, so let's have another quiz based on what you understood conceptually. Which types of aquifer materials would have highest storage capacity? So storage means how much, think of which one, which of the two parameters that we just learned. One is porosity, another is specific drainage or specific yield. So one of them is related to storage. Okay. So which type of aquifer material would have highest storage capacity? So I give you 4 options: sand, sandstone, limestone, or shell granite. And those materials, the properties are given here. All right, so raise your hand if your answer is A. Okay. I can't put a number, but I would say that more than 50% I raise for A. I know that in Zoom also we have some raised hands. Okay, what about this B? Nobody. C? No. D? All right, so you have 30 seconds to discuss with each other what answer you think, and if you disagree with each other, that way at least you have some conversation. All right, so you see the logic behind it. Porosity is a measure of how much pore space where water can fill. So storage capacity is related to porosity. So all I'm asking is which one is highest, which one has highest porosity. So these numbers are given here. As you can see, sand has 34% porosity. So if it's filled with sand, 34% are pore space. So that means you can fill with, if it is sandy aquifer, that would have highest storage capacity because it has highest porosity. But if I give it clay, clay has 45%. So then you will say clay has the highest storage capacity. But just because it has high storage capacity doesn't mean that you can extract all that water. So that depends on the specific yield. In fact, clay has the very low specific yield. That's the reason if you have very much clay soil, that is unconfined aquifer, the clay layer. All right, so one thing we learn about how much storage that can answer the previous questions, but most of the time it's not just storage. Also, you have to pump very quickly, right? Because you need certain demand. So what you do is you dig a hole, which is basically a groundwater well, and you assume that the water from the surrounding will dump into that well. And how fast the water can dump from surrounding to that well is determined by this formula. It's called Darcys law. Darcys laws predict how quickly groundwater can move from A to B. This. All right, so as you can see that the reason why groundwater moves is because there is a force that making it move. And that force is basically difference in height of groundwater. That height is called head, groundwater head, means how high the water is. So imagine how do you do that in real life? You take one of you, let's say two of you drinking beer, and from a container, okay, or whatever it is. I never drink beer, so I don't know where it is. Imagine there's a glass, okay, and you drill a hole, small hole, in two friends. One person is standing here and drinking beer, and drill a hole from the bottom, and let's say you are drinking beer, okay, and we are drinking from the same one, and then it goes to that pipe connected, right? So now who is going to drink most of the beer? If I allow it to, right? So if I'm drinking too much, obviously there's nothing going there. So the point here I'm trying to say is, whoever has the highest elevations, if that water will beer will move from top to bottom. Okay, so it drain from. That's why water move from mountain to ocean, not other way around. So the height of or the head of the water table height or the head determines where it is going to move. So that's the reason, as you can see, this is called hydraulic gradients. That's the driver. So if you dig a holes and see what is the water table height, wherever the highest height, water is moving from there to where is the lowest height. Okay, so that's what we call gradient, hydraulic gradient, or DH. Not DH, DH over DL. So if you move from one, let's say there is a two locations, you drill a hole, look for what is the head, HA, minus drill a hole, another holes, and see what is the hydraulic or the head over here, like here in these pictures. Imagine this is A and B. And the difference between the distance between A and B. Here the distance is a minimum distance. It's not in an angle. Okay. So that will be here. If you see in this picture, that will be H2 minus H1 divided by L. So just know that water moves from highest head to lowest head. Okay. So if you are looking for, imagine you are just for convention, x-axis and water is moving from that directions. That means the head will be much higher in the first and the second well, head will be lower. So another way to say is, as you increase the DL become positive, another way to say is as the distance increase, the head drops because the direction of water flow. So that's why DH over DL is always opposite sign. Okay, just think of that as a because moving from higher to lower. Okay. And Darcy's law Darcys law basically take into account for this hydraulic gradients and calculate how much flow rate you can have. So that flow rate is, this is the amount of water that you can withdraw from a well. That's the flow rate. This is flow rate. The unit will be liter per minute or cubic meter per minute or gallon per minute or gallon per seconds, all that is related to hydraulic head. This is hydraulic head, just we learned that. This is the driver of the force behind the water flow. It also depends on the area, because imagine you have a well, this is the basically well surrounding area, so the width of the well, okay, so that's where water is going to fill in. So imagine you put a cylinder inside the soil, and the cylinder has a lot of hole and it's on the side, so that's exactly basically the area. The cylinder area is where water can fill in. And then K is the hydraulic conductivity. Hydraulic conductivity is a property of aquifer itself. It's a measure of how fast water can move from one to another place. So that's, for instance, sandy soil, water can move very quickly. That's why if you pour water on a beach sand, you can't see them after a point. No, within a second, it's all going to gone. But if you pour the same water on, let's say, on a soil surface, it takes a while before water can get in. So that's because the K value is very different for soil materials. So there is a question, is dH over dl is hydraulic gradient? Yes. So this is, you're right. So dH is hydraulic head, change in hydraulic head, dl is the length. So dH over dl is hydraulic gradients. So if you take whole thing. Okay. Yes. Say again. Hydraulic head. So hydraulic head is basically the, if you the height of water from a arbitrary locations is called datum. Datum is basically, you are comparing, because if you dig a hole here or the well here versus another spot 10 miles from here, there is a reference point that you have to compare with. So that reference point is datum, and that's not defined in the sense that's known by USGS. So you have to ask them, what's the exact height from that locations. So that way you can calculate what's the the water table height. So this is basically here. Visually, that's. So the question is, does Q show the flow of water into the well? Yes. If you're asking for how much water you can withdraw, that's exactly the case. Okay. All right. So let's use Darcys law to solve a question on flow rate. A confined aquifer of 20 meter thick. So it says confined. Okay, so confined, unconfined, that's just the things to know. 20 meter thick, which is basically here given. Has two monitoring wells spaced over 500 meters apart along the direction of groundwater flow. So it says 500 meter distance. So the picture is given, so I don't have to draw it. So this is basically L or DL, however you want to define it. The difference in water level in wells is 2 meters. So this DH is 2 meters. The hydraulic conductivity is 50 meters per day. That's the K value. Estimate the rate of flow per meter of distance perpendicular to the flow. Okay. So it's saying that what is the rate of flow. So that's basically Q. Based on the Darcys law, you know this one. what you are asked basically is rate of flow per unit per meter of distance perpendicular to the flow. So that means it's saying is basically so it's basically saying the area is 1 meter per distance perpendicular to the flow. So if the flow is coming this direction, imagine it's coming across that surface. So it's saying that perpendicular to the flow, if you take per unit meter, how much water it can be exerted. So that's equal to K dH over dL. So K value is 50 meter per day. DH is 2 meter. DL is 500 meter. So that value would be 10, so 0.2. So this is the speed at which water is moving, 0.2 meter per day. But if you are calculating the flow, then if I leave it area here, so that's basically 1 meter times 1 meter. So area, yes. It's per meter. So it's basically saying that yes, the unit of the cross sections. Okay. Usually that you calculate for the well, not for this kind of thing. So well casing height, the diameter given, then you know the area. But here you can't. So that's why it says imagine it's moving perpendicular imaginary well, which is so wide that you are taking only one cross section. So this per meter comes from here. Okay, so is there any questions? Start window. Yes. You know, that's a good point. If your well is completely gone through the entire aquifer, then you have to calculate based on the width as 20 meters. So 1 meter as a cross section and 20 meter depth. So this area would become 20 times 1. So another way to say is the question was, imagine this one. The well is all the way here. That means water is coming from all sides, right? Then the area that we are collecting water is 20 meters times 1 meter on the side, right? So this become 1 meter. Because you don't know exactly how far the water is going into, so then you don't have that one. So check the book if it is assuming that it's gone all the way to entire aquifer. So think of this imaginary thing. Think of the well as a rectangular well, yes, not circular. Then it's become easier. One width is 1 meter, across the diameter is 1 meter, and then the depth is basically whatever the aquifer is. All right, so this is a conceptual question we covered before. I just want to put it here. Why clay is very difficult to, why it is so difficult to get For some reason, I cannot click this. There are some questions. Which are oh, Mike, yes, yes. Let me see now. No, sometimes it does happen. So otherwise, I'll just leave the mic here and speak without touching it. If you guys can hear it, then I'll just stay here. That way nothing is moving. All right, so why does water drain slowly in the clay even though it is highly porous? So as you can see over here, the clay has 45% porosity, but it doesn't have, the water doesn't move very quickly. The reason is, if you ever saw clay, now the clay is the same material that's you use to make ceramic clay, ceramic container. And the reason why they use ceramic or the clay in the ceramic, or that's basically synonymous, is because they are very fine particles, less than 1 micron size. And then these clays are basically, if you see under a microscope, they are basically like this. The gap between those widths is few nanometers. And at that very, very small space, water is held so tightly by capillary that you can't push water through. Even whatever water is there, you can't withdraw it. So water moves extremely slow. That's like maybe few millimeters in or few inch for entire years. Okay, so that means almost like it's not moving. That's one of the reasons clay is used as a liner materials for any landfill. So if you're designing landfill, you don't want the landfill leachate to get into groundwater. So they fill with clay because clay has its material property that doesn't allow water to move through. So the reason is capillary force. Capillary is, if you imagine it, the gap is water. That gap is filled with that water that holds so tightly that it doesn't move out. So that means even it has high porosity because they're so small that almost porous, because there is always a little bit water in between. So there is highly porous because of the fact that it's small and it's stacked against each other with some gap. That gap is making them porous, but that gap is unusable for water storage, water drainage. All right, so another thing you learned that hydraulic conductivity is something that you need to estimate how quickly water moves. And so hydraulic conductivity depends on many factors. Number one, depends on what's the gap. As I said, the hydraulic conductivity of clay is very low. The reason is the gap between those points is so small that water is very light capillary. So roughly you can say that if the clay, if the porosity normally has highly porous, that means there is more likely water will move much more frequently. Not just porous, but also the gap, the width between those the particles. So, with the larger particles, the gap between those particles are also large. Okay. So if your particle size increase, imagine you put two big large balls into a bucket. There will be a lot more gap left behind. That means if you increase the particle size, more likely the gap between them will also increase. That means the water will move much faster because there is less and less gap there also. Really compared to because of this. Chemical properties. Some kinds of minerals can actually stick with water molecules. So that means if they attract water, then water cannot move fast. That's related to chemicals. Biological is basically related to plugging. you have any soil, if you have any soil with a lot of bacteria, they form biofilm. They can also start clogging some of the pores. If there are more biofilm, that's kind of restrict the flow. If that can happen, hydraulic conductivity will decrease. Okay. If the biofilm increase, K would decrease. Okay, here is hydraulic conductivity. Then also hydraulic conductivity depends on water properties. If the water is viscous, then water will move slowly because there are a lot of more frictions. So that viscosity depends on temperature. So if your temperature is high, water is more likely lighter materials because it expands, less viscous. So that means your hydraulic conductivity will be higher. But that's very less practical significance because the viscosity changes is so little that you don't really account for that amount. So this is all given over here. All right, so now let's see the quiz before we break. Which type of aquifer materials would allow water to move faster? Sand, clay, and limestone. For some reason, I cannot click the chart window here. So if you see a question that's writing the address, you guys can let me know that question. That way I can answer that question. All right, so how many of you think answer is A? How about B? C? I didn't raise my hand. All right, so as you can see, all I'm asking is where the hydraulic conductivity is higher. Does it move faster when there is a K is higher? Okay. So as you see here, hydraulic conductivity is given. Sand is 41. You see, sand is 41. I'm just looking for this one. This over there. And then clay is a really small number, 0.0004. Limestone 0.041. That makes sense. But you can see if from the perspective, the clay is so small, almost like it doesn't move. That's why you know that too much confined. One last thing before we go to the break is what we learned so far is the flow rate. It doesn't say anything about how quickly water moves from A to B. Just says that how much water we can drain through that we are able to collect water. Okay? So the actual water velocity is basically have to divide the amount of response. So from Darcys law, we know this one equals K over here. We know from basic definition, if you divide flow rate divided by area, we get a velocity term. So in this case, if you do the extension, you get a velocity term, we call that Darcys velocity. Darcys velocity is not the actual water velocity. Let you know why that is. Imagine you are drilling a well, and you are measuring how much water dropped into the well. That's the Darcys flow. Divide by the area of the well, you get the Darcys velocity, the Darcys flux. That's not exactly how the water moves. Water doesn't move to the entire well. Remember, I take a cross section of the area. I think this is done. If you think the sand over here, so the moment I walk away, they can't hear it. So let me see. All right, let me force to stand here. If I move, let me know. I don't move. Okay. All right, so this is a, hopefully they can hear now better. As you can see, imagine the cross section. The soil is filled with that entire well casing. You'll see some of the soils are filled with water. Water doesn't move through the soil, it moves through the pore. Okay. So when you say this area is the entire area. Okay. But really the water moves to the area which is filled with water. Okay. And that portion of that area is filled with water is area times porosity. Okay. Only small fraction of the total area is filled with or water can move through that. So then that means you have to account for that. When you think of water velocity, you have to account for that surface area, for the area that water can move. So if you divide by Darcys velocity divided by porosity, you get the velocity of water. And so give you a practical significance where it is applied. So imagine you have a garden hose and you are pouring water through the garden hose. And imagine that's the completely empty, right? So that's why it's moving certain velocity. And I put my finger at least 50% of the garden hose. What do you see? The velocity of water. It's going to decrease or increase? Increase, because you are restricting now into 50% of the area. And then water has to move within that 50% area, so it will speed up to have the same amount of water coming per time. So the reason is as you decrease the size of the pores, water speed up to conserve the mass. So exactly the same thing happened here. The actual water velocity is much higher because it's not moving through the entire well area. It's moving through a small pore within that soil cross sections. So that's why if you are calculating water velocity, so that has to be seepage velocity or water velocity is basically Darcys velocity divided by porosity. Another way to say is K dx over dl. So this is the formula for water velocity. This is important because whenever you have pollutant mobility, you are comparing with the water velocity. Yes, so that A is not there. All right, so this is all kind of background. Let's take a break for 5 minutes because we lost a lot of times initially to set up the problems. When we come back, we solve these questions. And then we solve some question related to contaminants. Okay. All right, so we have less than 30 minutes. So let's solve some questions. All right, so this is another example questions where you can use Darcy's law to calculate the velocity of groundwater. Okay, so this is typically 50% of a long questions that you will have on a on midterms. So most of the time the question is how quickly a contaminants move, and with reference to how quickly a water itself moves. So 50% is what's the speed of water. So that's basically these questions. So let's see this one. Suppose an aquifer in example 12 has become contaminated upgradients of the two wells. Consider the upgradients well as a monitoring well whose purpose is to provide early detections of approaching plume to help protect the second and the drinking water well. So all it's saying is the second well is drinking water well, and the first well is more like a monitoring well to see when you have a pollution. How long after the monitoring well is contaminated would we expect the drinking water well to be contaminated? So you have two wells. The first one is a monitoring. At the moment it is polluted, you will get a signal that's saying that it's polluted. Then you have certain time before the second well will be polluted. Ignore dispersion, diffusion of the plume, that is not spread out. Assume that the plume moves in the same speed as groundwater, and ignore the pulling effects of drinking water well. So here it says that a pollution is basically saying how quickly water is going to move from one well to another. So the velocity of water is what is asking, okay, or the how quickly it moves. So let me write it properly. So the time it takes for water to move from one well to another one to say is 500 meters. How long it takes for water to move from 500 meters from one well to another, which is the distance between the well. So time is basically distance by velocity. That's something you know. Distance is 500 meters and velocity is something that you don't know, you have to estimate. So what's the speed of water that you just know? Velocity of water is basically this formula, Darcys law divided by this. Darcys velocity divided by porosity. So if we put this value here, by porosity, that means it's d times porosity, k dh over dl. So 500 meter is d, that's the distance. Porosity is given in the previous questions, which was here. The porosity was how much? This, I think this is the one. So the sand is 34% porosity. So porosity is 34%, assuming sand. Okay. Yes. Oh, aquifer has 35. You're right. Thank you. So this is 35% is porosity. Thank you. So all right. So everything else is given. Let's see. D is 500 meters. Thus the distance will move. Porosity is 35%, 0.35. K. K is whatever you calculate in 12. So that's the value. Question number 12. 12 is 50 meter per day. That's the hydraulic conductivity. 50 meter per day. DH is the change in head within that distance. Is you see over here that head is 0.2 or 2 meter divided by gradient is 500 meter. That means that's the change in head over that distance. All right, so your answer would be whatever that number you'll get in terms of day. Okay, because everything else cancel out. Now the second half of the question is how quickly contaminants will move, right? So here it says how quickly contaminants move because the assumption was contaminants move the same speed as water, but that's not the case for 99% of pollutants. Only pollutant which are non-reactive or conservative, that means do not stick with soil, they will move as fast as water. So for instance, chloride, salt water, they will not stick with anything else. So they move at the same speed as water. But if you are thinking of pollutant like, let's say, PCB, organic pollutants, they will degrade over time. They will also stick with soil. They will also stick with other materials in the aquifer. So that means they will move much slower because it will flow down with time. So you have to account for that other aspect of it. And that's basically the second half is groundwater quality. So this is the equation you can use to predict whether there is a location which is polluted by groundwater or not. For instance, if you see this particular news, click on the YouTube, you will see that this particular Air Force base, the people living around it start having cancer. And they thought, what could be the reason? And they found that there is a pollutant people use in the airport to extinguish fire is found in their drinking water. And they realize that's because of the groundwater is not really retarding that pollutants. And so how long before they found that this pollutant that used in airport, which is upstream of groundwater, is contaminating the groundwater well, which is downstream of that airport. So that's basically we are going to calculate using the formula that we cover. So a lot of times you see picture like this, which shows that how quickly groundwater plume is moving in ground. They present like this. All the red color over here, that shows the pollution, and the green is basically non-polluted water. Okay. So again, you can calculate groundwater flow based on this. Just we calculate that. You can calculate groundwater velocity if you know this formula. Okay. Again, I'm just going to write it. Distance over velocity. So distance is d. Velocity is Darcys velocity by porosity. So then that porosity will go up. So that's k dh over dl time porosity. Hydraulic conductivity. This is the same question as before, the one we just solved it. As long as you know all these values, this is hydraulic gradient. So everything is given. So this is dH over dl. I'm just writing quickly so that we can go to the next questions. This is porosity. This is d. Everything else is given. You're just calculating the speed. Okay. Now, as I said, if you really solve this in fundamental way, what makes the contaminants move is advection and dispersion. Advection means because water is moving, anything in water is moving with that. So advection is related to velocity of water. Depends on velocity of water. So if the velocity of water is moving faster, then the advection is much faster. Dispersion is mostly, think of if you put a drop of oil on water, it disperses very quickly. It has nothing to do with the velocity of water because water is not moving. So that dispersion occurs because of diffusion, and that diffusion can be because of mechanical diffusions as well as the fact that now something is blocking, so that it's just finding a way to move or spread. Okay. But pollution or the pollutant mobility can be also decreased because of a lot of other processes like adsorption. Adsorption means things are sticking on soil. So that's related to how sticky the soil is. You measure based on the adsorption coefficient. This is called KD. Okay. Adsorption. We'll get to the point. Coefficient, or how sticky a substance is. So if the KD is high, that means the pollutant is going to stick with aquifer material more likely. So if the KD is high, that means more adsorption. That means slowly it moves. It will not move as fast. So this is opposite to mobility. Redox or reactions. So this is basically reactions. If there is a reactions, the things are being destroyed. So that means the pollution you will not see in the other end because they are being reacted. It's like a PFR. Okay. So these are basically reactions. Reaction in water. This is basically reaction with the soil. Adsorption is basically a type of reaction that means it's just taking the contaminant on soil. It's not destroying pollutant, it's just removing pollutant from water. This is on soil. So as you see, this KD is mostly important because a lot of times aquifer soil is your protection, so that's where the things will stick on the surface. So how do you determine that KD value? Most of the time, KD is determined experimentally. So what people do is, if you want to measure what is the KD value, you basically take some amount of water. Let's say this is a certain volume of water. And it has this a volume of polluted water. So that means there is a certain contaminant is there. So initial concentration is C0. Initial concentrations. We saw this one, the adsorption very early in this class, not today class, but early in the first 3 lectures. So I'm just rephrasing it. So now what you do is you put some aquifer materials, some amount of soil with the mass M, you added it, and then you shake it. Mix it together for a while. When you mix together this pollution or the contaminant, some of the pollutants you're going to start absorbing on the soil. Okay. Because of that, the concentration is going to decrease. So this becomes C. That means this is C, the concentration is now smaller than what was initially. And rest of the pollutant has gone to the soil. So as the contaminant concentration increase in soil, the concentration in water will decrease. So you know this one. So that means the KD is basically concentration of pollutants, concentration of pollutant in soil or on soil because they are absorbing by concentration in water. Basically, after absorption occurs, this is what you are determining. So this is C. And what concentration in soil is basically what's not remain in water or what is removed from water. So this is basically initial concentration was C, final concentration was small c, and then this is the difference in concentration that's gone to the soil. But the total amount of mass that gone into soil is concentration times volume of water. So this is the mass of pollutant that gone into to water or the soil itself. And then if you know how much the concentration of that pollutant in soil, you divide the mass of soil. So this is the mass of soil. So that's basically the top portion is the concentration term for the soil. So normally you had this equation before, but you don't. This is just done experimentally. So that's the whole point of it. Okay. But normally that KD is given to you in your problem. You don't have to calculate that from anywhere. It's already given to you. Okay. And the point I'm trying to say here is this is basically concentration of pollutants. So mass of pollutant divided by weight of soil. That's the unit on the top. Then mass of pollutant volume of water. Mass of pollutant, same unit, so that means it's cancel out. So the unit of Kd is basically volume of water divided by weight of soil. Okay. So what you got here is, this is liter, let's say this is kilograms, so the unit is liter per kilograms. Another way to, it's going to write it properly. So anytime you see the Kd is given, that liter, that unit is liter per kilograms, because it cancel out. So this is just to show that now, because in the big problems the number will be given, but you will not know what is the Kd value. But if you see this unit, you know that's the unit of Kd. Okay, that's the only reason I show that. So what it means Kd? It means in how sticky a substance is, how sticky a contaminant is. So the Kd, it turned out, is the pollutant itself is a lot of organic pollutants. It's not really binding with all soil. It's only binding the organic carbon in the soil. So it turned out, if you know how much organic carbon is, you can actually calculate what is the Kd value. So this FOC is the fraction of organic carbon in soil. The reason we make that assumption is that the reason is the some of the pollutant, they only bind with organic, not the clay, not the other things that you see. So you only account for that. And this KOC is basically affinity of pollutant on organic carbon. The reason why this unit is, or this equation is used, is because imagine if you are trying to predict what's the, how quickly can pollutant move in aquifer, you cannot, you have a Kd value for that aquifer itself. If you want to translate to another soil somewhere else, you have to again measure the Kd. So it takes long time. So that's why people come up with this term. They say, okay, it doesn't matter because only bind with organic carbon. All you have to do is measure how much organic carbon in those soils. And then KOC value is constant for certain pollutants, as long as the organic carbon is very same. So then KOC value, if you know, you can apply for many aquifers with different amount of organic carbon in it. So that's just the concept. So in questions, FOC, KOC, all will be given to you as far as solving the problem, but just know why it is used. So again, the Kd, it's basically a measure of how sticky a substance is or a pollutant is. It depends on many factors. Kd depends on FOC and KOC. FOC is a function of aquifer materials, how much organic. KOC is a function of pollutants. Some pollutants are more sticky than some pollutants are less sticky. So if KOC is high, that means pollutants are more sticky to the organic carbons. Kd also depends on surface area. Because the adsorption is a surface active process, how much area is available, that determines the adsorptions. Okay, so if the particle size is small, surface area is high, that means more area for things to adsorb. All right, so now that we learned this one, let's solve one question from last year or few years ago midterms, then you know how to solve any question on groundwater. Before that, the quiz question, which of the following factor would not affect contaminant velocity in groundwater? Hold on, this is, I didn't really explain to this one, so let's hold these questions because you don't know what is bulk density is. Okay, so bulk density is, I'm just going to write it here. The answer is D, but we'll get to the point why it is the case. But you don't know what is bulk density. Bulk density You kind of know it, but all it means is mass of soil divided by volume of soil. When you say mass of soil and volume of soil, that's including the porous, including the pore space, including pore space. Okay. Not just the volume of soil. It's a soil grain. Okay, so the point here I'm trying to say is there is a mass balance equation. All I put is how much concentration of pollutant change in soil at any location if you take is a function of how much pollutants move into a locations or how much pollutant leaving that locations. That's the right side. Okay, the differential equation is a special for like in the form of space or x. The x left side is basically a concentration change in a function of time. So this is advection dispersion equations. We are not going to derive it, all that stuff. But all I want to say is you can predict the concentration of changes in any locations if you know how much pollutants is moved because of advection, which is velocity of groundwater, which is this, and how much pollutant is dispersed because of diffusion, which is here, and how much pollutants is adsorbed because of adsorption, and that's related to retardations. Retardation is based on adsorption. Okay, so these three factors. Anytime you want to predict change in concentrations, that depends on three things: how quickly groundwater is moving, because that's supplying that pollutants. That's velocity. How quickly pollutants is dispersed, okay, because that can dilute the systems. That's diffusion. And the third one is retardation. Retardation is related to how much things are being absorbed or reacted. Okay. And so that retardation, based on these equations, it turned out to be this. 1 plus bulk density of soil times Kd, which is the adsorption coefficient, divided by porosity. And what is retardation coefficient? Is basically velocity of water divided by velocity of pollutants. It's a measure of how slow pollutant is moving with respect to water. So retardation, if R equal to 1, that means velocity of pollutants is same as velocity of water. That means no reaction, no adsorption, nothing. It's a conservative pollutant. R is greater than 1, velocity of pollutant is greater than velocity of water. That means, or I'm sorry, this velocity is less than water. That means pollutant is moving very slowly. That's the whole reason retardation is more than 1. There is never a case retardation is less than 1. It's impossible. Okay. The reason is the pollutant will move at least the same speed as water, not faster than water. Okay. Because it is moving in water. It can't move faster than where it's like you can't outcompete the if you're anyway, doesn't matter. The point is that's the quiz question. Okay, so a lot of times I'll give a statement: retardation factor is less than 1, true or false. Those kind of question is that. So now, a lot of times in midterms, I'll ask what is the velocity of pollutants. Then you use this formula: velocity of pollutants is velocity of water divided by retardation factors. Okay. And retardation factor, you know already this number. So just now, a few minutes ago, we solved velocity of water. If you know what is the retardation factor, you exactly know what's the velocity of pollutant. And that's basically the midterm questions. So let's see one of the midterm questions, then you can solve it. All right, so let's solve these questions, and then in 3 minutes, which is, you will see this is that quick. A leaking groundwater storage tank has discharged the solvent trichloroethane into groundwater at a rate of 100 ml per day. To ensure that safety of water supply, the tank is removed to stop the source. A side investigation shows that subsurface aquifer materials consist of primarily medium sand with porosity. So again, anytime you see the number, just start writing. Porosity 0.39. Ball density, that's basically this. Gram per centimeter cube. And hydraulic gradient is 0.05. So this is dH over dl. Actual velocity of groundwater is 0.1 meter per day. So velocity of groundwater is, okay, so these are all given. The first question is, what is the Darcys velocity? Okay, Darcys velocity, you know, Darcys velocity by porosity is groundwater velocity. Okay, that's something you know before. So Darcys velocity is basically velocity of groundwater times porosity. Those numbers are given. If you see in the previous questions, just 0.1 meter per day times porosity is 0.39. What is the hydraulic conductivity of aquifer? Well, you know Darcys velocity is k dH over dl. So hydraulic conductivity is gradients divided by dH over dl. You know already these numbers, 0.039 divided by dH over dl is given here, 0.00. So now we are almost at 150, so that's the end of the class. So what I'll do is I'll just write the formula, then I can solve it later. So basically it says, what is the retardation factor? The second question is, what is the retardation factor? Retardation factor is 1 plus porosity. Everything else is given actually. Okay. So that's the same thing as KD is FOC times KOC. All these numbers are all given. What is the fraction of organic carbon? KOC. So you just put the value, get the answers. Okay. The last one is how far you expect things to move. So that how far a pollutant will move is velocity of pollutants times time for pollutants. Okay. So time, you know how to calculate from previous equation, and velocity of pollutants, you know, is velocity of is basically velocity of water times retardation factor. Then you just plug all the value, you get the answers. Okay. So I'll solve it in the slide, so I don't have to, you can check your solutions. Okay. But it's basically plug the value and get the answers. All right, see you next class.